right, we're going to continue on talking about reciprocal functions with quadratic reciprocal functions. So we already analyzed linear functions. Remember we said that any linear function, right, straight line, we can draw the reciprocal, right, where this is f of x. We can draw the reciprocal, 1 over f of x, by doing the following. First, we need to make sure we draw vertical asymptotes wherever we have x-intercepts. Oops. So remember, a vertical asymptote is a line we cannot have, right? Whereas an x-intercept is where my numerator is equal to 0. So that flip, that reciprocal action affects that value, meaning I cannot have points wherever my original function had x-intercepts. I put my invariant points at y equals plus or minus 1, right? Because those are the values that when I flip their values, they will not change. So I try my best to locate where positive 1 and negative 1 are on my graph, and I just make sure that my points connect at those locations. With quadratics, we're going to add in a new step here. So because quadratic functions have a maximum or minimum value, I need to make sure I plot the new max or minimum value. Remember, it's that transformation xy turns into x 1 over y. So that's going to be a key point that I make sure of. I have to pay attention to my vertex on these quadratic functions. Then I kind of go along with those trends, right? Wherever my original function was increasing, my reciprocal function decreases, right? As this was going up towards higher y values, the reciprocal should decrease towards lower y values. And as I get close to that asymptote, right, as my y values are decreasing, I'm going to see my reciprocal function increase up towards infinity. I'm going to see it decrease down towards negative infinity on the other side as I approach 0. And then I'm going to see it increase up towards 0 as I approach that x-axis. And remember, I have a vertical asymptote. I also have a horizontal asymptote at y equals 0, because every one of these functions will have a numerator of 1. I cannot get a value of 0 out of my answer. And again, any plotted point has to change from xy to x 1 over y, because I can choose those independent x's myself. The result of those y's is what I'm seeing change. So when I have those quadratic functions with a maximum or a minimum, right, I have that vertex, I know that really large y values become really small when I take the reciprocal. Really small values become really large when I take the reciprocal. So what ends up happening is that a maximum value at my vertex turns into a minimum on the reciprocal. I'm going to say on f of x turns into a minimum on 1 over f of x. And then I have a little caveat here of that section, because these reciprocals have kind of those distinct areas, right? I have those areas separated by those vertical and horizontal asymptotes. So my maximum will turn into a minimum. My minimum, if I have a minimum value, right? So I'm talking if I have a quadratic that opens down versus a quadratic that opens up, so those maxes are mins. A minimum value at my vertex on my original function means that it will become the maximum value on the reciprocal function. And again, of that section, right? And this is because those vertical asymptotes will divide things up. So what I just want to make sure of is that I make sure when I'm plotting this graph, you need to plot your new max / min, right? You need to tell me that PQ is going to turn into P1 over Q, right? That vertex is an important point that we need to make sure we're accurately plotting. So let's sketch our first reciprocal function. And again, we're going to base this off of that original function first. I'm going to talk about just the regular parabola x squared minus 4. I know how to sketch these from our RF11.2 unit. And then I'm going to use that to help me strategically sketch the reciprocal function. So again, this is my equation. This is f of x, right? I can call it y, I can call it f of x just to specify it's a function. So if I want to take the reciprocal of this, I just put the whole function in the denominator. Having those zeros, right, those x-intercepts, as we saw yesterday, are super helpful for finding those vertical asymptotes. So if I look at my original function, if I look at y equals x squared minus 4, I can find those zeros, right? Remember, those are also called roots. Those are our x-intercepts. Those are also our solutions for when y is equal to 0. So I can solve the equation 0 equals x squared minus 4. I can solve this by bringing that 4 to the other side, or I can factor, right? Remind yourself this is a difference of squares. It's an x plus 2 and an x minus 2, which means that each of those factors will give me a different solution. There's a solution, or an x-intercept, at -2. There's also a solution at +2, right? So the zeros, or the roots, are -2, 0, and +2, 0. When I talk about the non-permissible values of my reciprocal function, now I'm asking, when is this denominator equal to 0? Which our denominator should look familiar because I just solved it equal to 0. So if I was to look at the same thing, x squared minus 4, minus 4 now cannot be 0. That's going to give me the same solutions, right? X plus 2, x minus 2 cannot be 0. That means x cannot be -2, and x cannot be +2. Because those non-permissible values are equivalent to the zeros of my original function. So let's start by sketching x squared minus 4. So I can sketch these quadratic functions in vertex form pretty easily. This one is in vertex form, right, because it has actually no x term in the middle. It's the same thing as if I said x plus 0 or x minus 0 squared minus 4. This thing has a vertex at 0, -4. It opens up, and it has a stretch factor of 1. So I can use that 1, 3, 5 rule to help me sketch the next few points. So if I go over 1 unit, I go up 1. If I go over 1 more, I go up 3. If I go over 1 more, I go up 5. And the same thing happens in reverse on the other side of my vertex. If I go left 1 from my vertex, first I go up 1, then up 3, then up 5. And so that'll allow me to sketch this quadratic parabola. Notice that it has those x-intercepts where I said they would be, right? At +2 and -2. So that means when I go to sketch, so here's this function, this is y equals x squared minus 4. When I go to sketch the reciprocal function, I'm going to start by putting those vertical asymptotes in. And I'm going to label them with their equation, x equals -2 and x equals +2. Because those are the points that now cause division by 0. It was a 0 on top when it was a quadratic. Now it's a 0 on the bottom now that it's a rational. So step 1, I sketch my vertical asymptotes at those x-intercepts, right? Or those NPVs. Those are the same points as we just saw. Next, I'm going to plot my invariant points. And remember, those are at plus or minus 1 for my y value. So remember, I'm zooming in here. I'm worried about what's happening at +1 and -1 for y. It's not going to be a nice point, but they're going to meet here in 2 different places when y is +1, because my quadratic function has 2 different x's where it equals +1. It's also going to meet at these 2 points inside the asymptotes between -1. Now that it's a quadratic, I have one more step to do here. I'm going to make sure I take my vertex and I transform it using that xy turns into x 1 over y. And so my vertex right now is at 0, -4, right? Those are my p and q values. So my new reciprocal point is going to be at 0 and then -1/4. So I'm going to do my best to plot that here. It's going to be pretty close to the axis, but that's my new point in here at 0, -1/4. And then I have those trends. So as my original function is decreasing, right? So parts like this, where I'm getting to smaller y values, my reciprocal function will increase. And it kind of looks like a parabola itself. It's just a little more flattened out, right? Because if I think about points like here and here, those are at -3, so the reciprocal is up at 1/3. Then I worry about the parts that are increasing. So right here and right here, these tiny little segments are getting closer to being 0. So their reciprocals are going to get farther away from being 0. So I'm going to see it hug those asymptotes just like it did before. Whoops, do a better job of that. And get really close but never actually reach -2. And get really close but never actually reach +2. I also have a whole other section of this graph up on the left and up on the right, where I have the same trends. As I have this tiny section here where I'm decreasing towards 0 in my reciprocal function, and then I have this section here where I'm increasing, right? Which means that the reciprocal function increases. Same thing on the other side. This tiny section where I'm decreasing, my reciprocal increases. And then as I go out further left and my original function was increasing, my reciprocal function is decreasing. And just like in all of these, I will have a horizontal asymptote. I will never be able to cross 0 in this unit because of the reciprocals we're working with. So those 3 purple lines make up the whole function y equals 1/x² minus 4. Let's talk about these functions a little bit. Let's talk about the domain and range. So my original function, my quadratic function, this thing had a domain of all real numbers, right? That was pretty nice. Right, so the domain is all real numbers, just like any quadratic function. The range was all of those values that were greater than my minimum, right? -4 and above, right? Because I had that lowest value at -4, and I just continued to increase along my y values, and it went up forever and ever. So when I look at my reciprocal function, my domain is close to going on forever. It's going to go all the way left. It's going to go all the way right. But there's a few hiccups in the middle, right? And that's my vertical asymptotes. So my domain is all x's as long as I don't consider those non-permissible values or those vertical asymptotes. So I can have every single x value. I can have 1.99999. I could have -1.99999. I can have 2.0001. But I cannot have +2 or -2, right? And those are my NPVs. And now when I look at my range, things are going to be a little bit funny here. Things are going to be a little bit odd because I have a bunch of different sections of this graph. I have these 2 upper segments, right? This arm and this arm. And I would describe those as being y's such that y is greater than 0 with a strict inequality, because I can't actually reach that x-axis, but I have every value that is greater than 0. So I have y such that y is greater than 0, but then I also have a bottom segment here. And when I look at this one actually doesn't quite reach up to that x-axis. It's not actually going to try to get to 0. It doesn't reach that asymptote because it has a new maximum value, right? It has a maximum value of -1/4. So that's going to show up in my range by saying y is less than or equal to, because it does hit that point. It's not an asymptote, it's just a new maximum value of -1/4, and it's all real numbers. So that's kind of a funky way to have to describe it because I have those 2 different segments. This is describing my 2 upper arms, and this is describing my lower half, whatever you want to call it, that has a maximum value, right? It was my minimum before, now it's my maximum. So that plays into my range here. And so if I want to sketch another quadratic, I'll go ahead and do that. This one is in standard form. So again, I could sketch this by plugging it into my calculator. I could complete the square and put it in vertex form. I can plot some of those points and try my best to kind of solve for those x-intercepts and really play into the symmetry of a quadratic. So let's sketch this quadratic first. It would be helpful if I knew my x and y intercepts to help this sketch. So I'm going to solve for those x-intercepts first. I can factor this, x plus 3 and x minus 1, multiply to negative 3, but still add to positive 2. So I have x-intercepts at negative 3 because of that first factor, and positive 1 because of that second factor. So my graph already has those asymptotes in, right? But I should solve for those. I also have a y-intercept at negative 3. Right? And if I'm looking at the symmetry here, I know that the axis of symmetry is going to run right between those two x-intercepts. So that can help me kind of just plot these points a little nicer and sketch this without using my calculator, right? Because I know that if this point is here, I have to have that symmetry. So 1 over from my other x-intercept also has to be a negative 3. And then because I had, again, that a value of 1, I'm kind of doing that 1, 3, 5 rule in reverse. This was my 3. So to get to my next point backwards would be the 1. Then I could do that last step, go up 5 when I go over 1. And then I've sketched this parabola. But I could also, right, I have access technology. I can plug this into my graphing calculator and plot some points. I can make my own table of values. Any way that's going to help me sketch y equals x squared plus 2x minus 3. So now I'll sketch my other function. I'll sketch y equals 1 over x squared plus 2x minus 3. I already solved for those x-intercepts, so I know this thing has non-permissible values at x equals negative 3 and x equals 1, because that's what my factored denominator would look like. Right, same thing. It's an x plus 3 and an x minus 1. So I can sketch in those vertical asymptotes to start. Right, they're already there. I have an x equals 1, x equals minus 3. I could also, minus 3, could also sketch in that horizontal asymptote just to remind myself I'm not crossing that x-axis. I'm going to sketch my invariant points. So at positive 1 and negative 1, again, these are not at nice x values, but I do just make sure they meet when y is positive 1 and y is negative 1. Then I'll find my max or my min, right? I previously had a minimum of vertex at negative 1, negative 4. So now I'm going to have a maximum at negative 1, negative 1/4. Coincidentally, again, the same point, right? This was a min, so this is going to be a max. So that can help me sketch kind of that downward trend of the middle section here, because I know if it's a maximum, it's decreasing from there and hugging those asymptotes. I know that up top, I'm going to go the opposite way that my original graph is going. As I increase, I'm decreasing, right? So as I go further left, my parabola arm was going up. I make my reciprocal arm go down. As I'm getting close to that asymptote, again, it's a tiny section to describe, but those values are decreasing. So I see my reciprocal do the opposite and increase. And so these purple lines, again, are 1 over x squared minus plus 2x minus 3. For practice, let's state the domain and range again of this thing. So the domain would be x such that x is not my NPVs. And that's how it's always going to be. X is not NPVs. So in this case, I say x is not negative 3 and positive 1, but it is everything else. And my range is y such that y is greater than 0, strictly, because then I'm hugging the asymptotes. I'm trying to get as close to 0 as possible. But then I'm also less than or equal to 1/4, because that's my new maximum. Right? So just like I would have described the range of a quadratic this way, if it had a maximum at negative 1/4, I do the same thing. I just have a separate section as well, a new segment. And so there's a few other cases that these quadratics might look like that we're not going to analyze here. But if I had a parabola that opened down, its reciprocal graph is going to look really similar, except I'm going to have that kind of flatten out reciprocal part up top. And then the two arms are going to be on the bottom half. Right? So it's just a flip of what I had. I still have a horizontal asymptote at 0. I still have vertical asymptotes wherever those x-intercepts are. Right? So I can see this graph open down as well. Notice that's going to affect my domain. If I have a quadratic function that only has one x-intercept, what that means is I'm going to end up with only one vertical asymptote. And so what my reciprocal graph is going to end up looking like is it's going to still curve. It's going to look kind of like those linear ones did, but it kind of looks like a little volcano because I have both of my arms increasing, whereas a linear, I have half of it in the negatives, half of it in the positives. Here, my whole quadratic will either all be above the x-axis or all be below. And I no longer have a maximum or minimum because that became my vertical asymptote. That became the point I cannot have. And then the last thing is if I have a quadratic that doesn't ever actually reach the x-axis, so I could have something up above like this, it's still that same idea that let's say this point, this minimum is at 3, let's do 5. The reciprocal of that would be 3/1/5. And that would become a max because this is my min. And so I see this weird kind of like anthill feature where it still has that horizontal asymptote at 0. It has no vertical asymptotes because there's no x-intercepts, but it kind of increases like a little molehill and then goes back down. Right? Because as I see this segment increasing, this segment needs to decrease. And as I see this segment increasing, this segment needs to decrease. And that max becomes the min becomes the max, vice versa. Right? But for the most part, we're concerned about these basic quadratics that have two x-intercepts, and we're looking like one of these two functions. So just like before, I can reverse engineer this process and tell you my original quadratic function, as long as I follow those guidelines, that my vertical asymptotes are my original function's x-intercepts. Right? This is on my reciprocal function. This would be on my regular function. So this thing has x-intercepts at -1 and +3. This thing also has a minimum or a vertex at this point. When I take the reciprocal of that, it becomes 1 over -0.25. Right, which is 1 and then -4. So I'm going to plot those somewhere else. I'm going to move this. So I have a point now at 1, -4. So my max and my min are swapping places for my vertex, right? Again, just the idea that 1 -0.25 turns into 1 -4. So now that I have some points, I can draw this. I can connect this graph. Let me pick a consistent color. I also should make sure I'm trying to hit those invariant points at +1 and -1, just to make sure it's as accurate as possible, because we're really going off trends for a lot of this. Right, so making sure that while I'm hitting those x-intercepts, I'm also hitting at +1 and -1 for y. And then the last thing is I want to give the equation of this graph. And we've done this before. We know easiest is in vertex form. You also could do this in factored form now that we know how to solve these things. But I have vertex form here. I have some xy coordinate. I have some PQ. I'm doing this wrong. I have a PQ. So I'm going to put that into P and Q. I also have multiple xy's. I could do this one. I could say 3, 0. I also could do -1, 0. I have lots of options. I just have to put in any one of these points as long as it's also not my vertex. So I have to pick a second point. So I'm going to put in, let's say 3, 0 for x and y. So I'm going to get something that looks like 0 equals a 3 minus 1 squared minus 4. So 0 equals a 2 squared minus 4. I'm going to add 4 to both sides, a times 4. So in this case, a is equal to 1. I should always solve for that though, just so I'm super sure. I don't want to assume. And then I'll give you my equation in vertex form as the question stated. It's an a value of 1. It's an x minus 1 for x minus p squared minus 4. So that's our whole reciprocals function unit. Really the main ideas are making sure you can sketch 1 over f of x given f of x when it's a linear or a quadratic. Right? And you have a good idea of all of those kind of new terminologies we've had. So we have invariant points, we have vertical and horizontal asymptotes, and how all of these things affect our domain and range. Right, so making sure we can go both directions. I can start with a regular function and sketch a reciprocal. I can also start with a reciprocal function and sketch an original function, talk about equations, talk about invariant points, talk about asymptotes, talk about the domain and range of these things.